Anyone who has ever managed a conventional stick frame build understands that the framing stage is, well, it's essentially a massive exercise in logistical
Oh,
friction.
absolutely. It's a headache.
Right. You are coordinating a lumber package drop, a crane for the roof trusses, specialized framing crews, sheathing crews, and you are constantly fighting the weather.
Yeah, just rushing to get the structure dried in before moisture degrades the OSB. It's a highly complex orchestration of just all these disparate materials and trades.
Which brings us to the focus of today's deep dive. We're looking at a system that attempts to compress that entire multi-layered, multi-trade process into a single structural step.
Right.
Our sources today are the official architectural FAQs and real-world customer service call transcripts from a company called EZ Log Structures.
And what we're really analyzing here is a hybrid building system, one designed to let a really minimal crew assemble a permanent structure in a matter of days.
Yes, and they're doing this without installing a single sheet of interior drywall, without any structural plywood sheathing, and without requiring any heavy machinery on site.
Which is huge for you, the listener, whether you're a contractor trying to optimize your labor matrix, or a developer planning out some ADUs, or even if you're just dreaming of building a full 3,000 square foot primary residence. This methodology is going to challenge basically everything you assume about modern construction.
It really forces a reevaluation of what is actually structurally necessary, right?
Yeah.
Versus what's merely conventional.
Exactly.
And as a quick logistical baseline before we dive into the engineering,
Sure.
the company's manufacturing and milling operations are based in Europe, specifically out of Poland and Estonia. But they ship these complete building kits directly to the job site all across North America.
Which is pretty impressive logistics on their end.
Right. Okay, let's unpack this, because the foundational premise of this system really hinges on the core material itself. When the transcripts mention a log structure, you naturally think of,
A cabin, right, like a rustic, unpeeled timber cabin with chinking.
exactly, the Abraham Lincoln kind of look. But looking at the schematics, this is a highly milled, precision-engineered product.
Yeah, honestly, the term log is almost a misnomer here. What we're actually looking at are these interlocking, precision-milled, solid wood components, and they're 2 3/4 inches thick.
Wow, that's substantial.
It is, but the critical factor is actually the specific biology of the timber they use. They rely on Nordic or Baltic spruce, the Ciabies species.
Yeah, I noticed the transcripts were incredibly specific about sourcing from that region. From an engineering standpoint, why does the geographic origin of the spruce even matter? Like, why not just use local pine?
Well, it fundamentally alters the specific gravity and the dimensional stability of the lumber. You see, Baltic spruce grows in the extreme cold of northern Europe.
Okay.
And that restricted short growing season means the tree adds mass at a fraction of the speed of, say, southern or coastal timber.
Ah, so it's a slow growth wood.
Exactly. If you look at a cross-section of this spruce under a microscope, you'll see a really tightly packed cellular structure. It has like 8 to 12 times the number of growth rings compared to the standard North American spruce, pine, or fir lumber that we normally use for framing.
Right, so that drastically tighter ring ratio translates to a much denser, heavier component.
Yeah, the density is a major factor. But the true advantage here is the dimensional stability.
Because it doesn't warp as much.
You nailed it. Because the growth rings are so tight and the knots are remarkably small, this timber is just far less prone to warping or twisting or checking when it's subjected to, normal moisture changes.
Which I guess is pretty crucial if you're basically building a giant puzzle.
Right, you're dealing with a premium structural material that takes complex tongue and groove milling with just incredible precision, which is non-negotiable when the wood itself forms both the structural wall and the finished interior surface.
Wait, so if I order a house, does it just show up in a box?
Pretty much. It arrives flat-packed in a standard shipping container.
That's crazy.
It's essentially an adult-sized, highly engineered mechanical puzzle. Every single wall component is numbered and sequenced for assembly.
And reading through the FAQs, it looks like the kit provides almost everything required to reach the dry-in stage, right?
Oh, absolutely. The container is a nearly complete exterior envelope ecosystem. Beyond just the numbered wood, it includes heavy-duty interior and exterior doors, featuring these multi-point European locking mechanisms.
Well, right. These aren't just standard deadbolts,
No, not at all. They engage the door jamb at 3 or 4 separate contact points.
which actually makes perfect sense for a solid wood structure, Because even with Titrine Baltic spruce, you're still going to have some minor seasonal expansion and contraction.
Right. Wood is going to move a little bit no matter what.
So a standard single-point lock might misalign slightly over the seasons, but a multi-point system guarantees this uniform, weather-tight seal against the stripping, regardless of microscopic shifts.
Exactly. That level of hardware tolerance is a huge theme in their components.
Hmm.
The kits also incorporate these double-glazed tilt-and-turn windows imported from Spain.
Oh, those European tilt-and-turn windows are phenomenal pieces of engineering.
They really are.
I was reading a customer service transcript where a builder realized these specific windows don't even use a fixed center mullion. Like, you can unlatch both sashes, open them fully inward, and you just have this massive unobstructed opening.
Yeah, you could literally pass a sofa right through the window.
It completely changes the accessibility of the space.
Mm.
But, sourcing premium hardware is only half the equation. The actual site assembly is where this system deviates wildly from traditional framing.
Oh, for sure. It's a totally different mindset.
Because they claim that a structure this robust requires virtually no heavy machinery, which just seems structurally counterintuitive. Let's break down this step-by-step assembly process.
Yeah, the assembly logic here is rooted in mechanical leverage rather than brute force. So the initial phase is entirely conventional. You still need a standard load-bearing foundation. Typically, that's a monolithic concrete slab or a traditional wood joist subfloor.
Okay, so normal foundation. Then what?
Then you apply a robust capillary break. That's a moisture barrier like heavy flashing or asphalt starter shingles, just to decouple the structural wood from any concrete moisture wicking up into it.
Got it. So once that capillary break is down, you anchor the first two base courses of the spruce right into the foundation, and the sequential stacking just begins.
Right. You literally just look at the blueprint, grab the component with the matching number, and slot it into the deep tongue-and-groove channel of the piece below it.
But obviously, you can't just rely on gravity and a milled groove to hold a house together. Like, what about wind shear or uplift?
Yeah, that's where the fastening comes in. The vertical integration relies on continuous mechanical fastening. So as you stack the courses, you secure each row to the timber directly beneath it.
Using what, just normal screws?
No, you use an 8-inch structural lag screw driven approximately every 3.5 feet along the entire wall.
Wow, okay, so you are essentially post-tensioning the wall as you build it. You're creating this continuous vertical steel spine that binds these separate horizontal pieces into a single monolithic wall.
Exactly. The screws are what resist the uplift forces, but what's fascinating here is how the lateral loads are handled. It all comes down to the interlocking corner notches, what the manufacturer calls the horns.
Oh, the parts that stick out at the corners.
Yeah. When these perpendicular walls intersect at the corners, those milled notches overlap. And as you tap them into place, they function literally like a structural zipper.
A zipper, that's a great way to picture it.
Yeah, they force the walls into perfect vertical plumb as you snack, and they provide massive racking resistance against wind or seismic forces. It completely eliminates the need for any exterior structural sheathing like plywood.
That is wild. Okay, so that answers the sheer strength question. Moving up the assembly, the roof framing is another area where they've really stripped out the complexity.
They have. In a conventional build, the roof structure usually requires a crane to hoist up those heavy, complex engineered trusses.
Right, which is a massive hassle and expense.
But here, the internal partition walls, like the solid wood walls separating the bedrooms or the bathrooms, they are actually pre-cut at the factory to match the exact pitch of the vaulted ceiling.
Wait, really? So the internal walls just go all the way up to the roof?
Yes, they stack all the way up and basically serve as the load-bearing points for the roof system itself. So rather than a messy web of trusses, the design utilizes glulam purlins.
Glulam purlins, those are the glued laminated timber beams, right? The ones that can span really long distances.
Exactly. These purlins simply drop into pre-notched pocket at the apex of the gable and along those sloped partition walls. Once they're seated, you just lay the tongue-and-groove roof decking perpendicularly right across them.
So the load is transferred evenly down through the solid wood interior walls and the exterior walls, right straight to the foundation.
Yep, it's incredibly elegant engineering.
And the tool requirements. The transcripts emphasize that because all this milling is finalized in the European factory, there is virtually zero on-site cutting required.
Right, you aren't out there setting up a complex miter saw station and measuring every cut.
So what do you actually need to build this thing?
The primary tools are just high-torque drills for those 8-inch structural screws and a fine-tooth handsaw. But the saw is purely just a backup for the spare unnotched logs they give you, just in case something gets damaged in shipping.
That's amazing. Just a drill and a backup handsaw.
Well, there's one more thing. The most interesting tool mentioned in the builder transcripts is actually a heavy-duty C-clamp,
A C-clamp. What for?
because it's solid timber. And regardless of the species, a 20-foot span of wood might occasionally have a slight torsional twist to it.
Right. It might not lie perfectly flat.
Exactly. So the builders say to set one end of the log into the groove, attach the C-clamp to the elevated end, and use it as a lever. You just twist the timber mechanically until it's plumb and drop it into the channel.
That is such an elegant, low-tech solution to natural material variance. So by removing the measuring, the cutting, the heavy lifting, and the specialized trades, the velocity of the build cycle has to be completely transformed.
Oh, it's night and day. The case studies in the sources note that a 3-person crew can take a 1,250-square-foot bungalow from the foundation to the dry-in stage in just 8 to 12 days.
8 to 12 days, that's insane. Dry-in meaning all the walls are stacked, windows and doors are in, and the roof deck is papered.
Yeah, ready for siding and roofing. But, this timeline compression does introduce a critical design challenge.
Okay, what's the catch?
Well, a solid 2 3/4-inch wood wall, while structurally formidable, does not meet the R-value energy codes required for primary residences in most North American climate zones.
Oh, right, because it's just wood. You need insulation.
Exactly. The structure needs supplementary insulation, and you also need a pathway to run all your electrical wires and plumbing pipes.
And this is where the methodology pivots from, like a simple, heady timber cabin into what they call their hybrid system.
Right?
The solution is remarkably straightforward, though I bet it feels completely backward to a traditional framer. Once the solid wood structural shell is fully anchored, you attach standard 2x6 dimensional framing lumber vertically to the outside face of the walls.
Yeah, you're essentially building a non-structural skeleton completely around the outside of the finished house.
And by placing that framing matrix outboard of the structural wall, you create this uninterrupted cavity. So the electricians and plumbers can run all their conduits, switch boxes, and pipes right through that exterior stud cavity.
Without ever having to drill through or mess up the beautiful solid spruce interior wall.
Right. And after the rough ends are inspected, those cavities get insulated. Looking at the sources, the manufacturer strongly recommends using closed-cell, high-density spray foam.
Yeah, the closed cell foam is brilliant here because it performs a dual function. It gives you exceptional thermal resistance, obviously. But more importantly, it acts as a continuous vapor and air barrier. It basically hermetically seals the whole building envelope.
I was waiting to see where the OSB or plywood sheathing fit into this exterior wrap. And looking closely at the installation guides, it just doesn't exist.
No, it doesn't.
There is zero plywood on this entire building. You attach the exterior siding, like a thick wood siding, or even an extruded PVC composite directly to those exterior studs.
Right. In traditional platform framing, a wall made of 2x4 studs has no real racking resistance on its own. It relies completely on the nailed plywood skin to keep the building from folding under pressure.
But because the interlocking Baltic spruce horns are already providing way more shear strength than you even need, the exterior studs are strictly just there to hold the insulation in the siding.
Exactly. The plywood is structurally redundant, so they just engineered it entirely out of the process.
Which creates a really fascinating architectural dichotomy. Because if you use, say, conventional PVC siding, that exterior wrap completely hides those interlocking corner horns.
Yeah, from the street, it just looks like a standard suburban house, maybe a nice Cape Cod or a Craftsman.
The siding takes all the weather, shedding rain and UV exposure, with basically zero maintenance. But then the moment you walk through the front door, the aesthetic completely flips.
Because the interior experience is totally defined by that exposed structural timber. Since the insulation and the wires were all pushed to the outside, every single interior surface, the walls, the vaulted cathedral ceilings, is solid, finished Baltic spruce.
Achieving that level of exposed architectural woodwork in a conventional build would require a massive finishing budget.
Oh, astronomical.
Here's where it gets really interesting, though. Choosing to leave that solid wood exposed on the inside isn't just an aesthetic choice. It fundamentally alters the building science of the space.
It really does. It unlocks some surprising superpowers compared to drywall.
Let's talk about the physics of moisture management and mold prevention first.
Okay, so the vulnerability of a conventional stud wall is all in its thermodynamics. A stick-framed wall is basically a hollow cavity filled with fluffy insulation, capped on the inside by a half-inch drywall.
And drywall offers basically zero thermal resistance.
Right, so in a cold climate, if cold air gets past your exterior barrier, it penetrates the cavity and makes the back of that drywall freezing cold.
And when the warm, humid air inside the house, from cooking, showering, or just breathing, touches that freezing drywall surface, it hits the dew point.
Exactly. Condensation forms right inside the wall cavity, soaking the paper facing of the drywall, which creates the absolute perfect biological incubator for black mold.
Ugh, a nightmare. But the hybrid system redesigns that thermal gradient completely.
Yes. By insulating the exterior with high-density spray foam, the thermal break is pushed entirely outside the structural envelope. The 2 3/4 inches of dense Baltic spruce just sit at the ambient temperature of the interior room.
Because wood possesses substantial thermal mass and low thermal conductivity, you basically eliminate those freezing cold spots in the corners of rooms that trigger condensation in the first place.
Exactly. And beyond just eliminating cold spots, the unsealed interior spruce actually functions as what the sources call a vapor bank.
Wait, a vapor bank?
Yeah. Wood is naturally hygroscopic, meaning in a humid environment, the cellular structure of the spruce absorbs the excess moisture from the air, banking it inside the timber.
Yeah, wow.
And then as the air in the room dries out, like when your heating system kicks on, the wood slowly off-gasses that banked moisture back into the room.
So it acts as a passive mechanical humidity regulator. It's actively working to keep the indoor climate right in the sweet spot where mold spores can't propagate.
Precisely. The house breathes.
The second superpower is fire resistance, which honestly sounds like an oxymoron when we're talking about a structure built entirely out of wood.
It does sound crazy, right? The instinct is that an all-wood house would be way more dangerous in a fire than a normal home.
But the physics of combustion paint a very different picture. The critical factor is the surface area to mass ratio and oxygen availability, right?
Yes. A conventional stick-framed house is just dimensional lumber surrounded by vertical, oxygen-rich cavities. When fire burns through the drywall, those stud bays act exactly like chimneys.
The draft just pulls the oxygen right up the wall.
Yep. It accelerates the combustion of the framing, leading to rapid structural failure.
But the hybrid system eliminates those interior hollow cavities entirely. The core is solid mass.
And when you apply intense heat to a dense, solid timber surface like this Baltic spruce, the outer layer undergoes pyrolysis and it chars.
And that char layer is actually a highly effective thermal insulator.
Right. It drastically reduces the thermal conductivity of the wood, shielding the inner core from the heat and basically suffocating the combustion process because the oxygen can't penetrate deeper.
It's the exact same reason heavy timber beams in historic warehouses often survive catastrophic fires while the steel brackets melt. The wood actively generates its own fire-retardant shield.
Exactly. The structural degradation slows down to a crawl, maximizing the time people have to evacuate safely.
Okay, let's pivot to the final superpower highlighted in the transcripts, the economics. The claim is that building an easy log structure to the dry-in stage costs 30 to 50% less than achieving that exact same stage with conventional framing.
That's a massive difference. And if we connect this to the bigger picture of construction economics, those savings are entirely achieved through a ruthless elimination of labor redundancies.
Because the material costs themselves are pretty competitive.
Right. It's the labor matrix where the real disruption happens. Remember, the kit arrives fully pre-cut, numbered, and ready to go.
You are systematically deleting entire trades from the critical path. You don't need a crane operator for trusses. You don't need a crew to nail off the OSB.
And most significantly, because those structural walls are also the finished interior walls, you entirely eliminate the drywall phase.
Right. You bypass the hangers, the tapers, the mudders, and the painters.
Drywall requires so many different mobilizations. A crew hangs the board, and they tape it, wait for the mud to dry, sand it, apply a second coat, wait again, sand again, and prime it.
It adds weeks to a construction schedule.
Weeks. And in commercial development, the carrying cost of a construction loan makes time literally the most expensive commodity on the site.
The transcripts reflect this perfectly. One of the high-volume builders noted that with a dedicated small crew, they can dry in 3 or 4 of these hybrid structures in the exact same calendar window it takes to frame and dry in just one single stick-built house.
That is just incredible scale.
And when that hybrid structure is dried in, the interior vaulted ceilings and the interior doors with all their hardware are already permanently installed.
It introduces this manufacturing predictability to a sector that is notoriously chaotic. By shifting all the complex measuring and cutting to the milling factory in Europe, the site assembly becomes highly resistant to weather delays, scheduling conflicts, and the massive material waste that usually plagues framing.
So what does this all mean? We've analyzed a methodology that just completely bypasses the complexities of composite framing by utilizing dense, slow-growth European spruce.
Shipped flat-packed right to your site.
Right. And this system empowers a small crew, equipped with just standard drills, a handsaw, and a C-clamp, to assemble a heavy timber structure in a fraction of the traditional timeline.
And by wrapping that solid core in an exterior matrix of studs and closed-cell foam, the design achieves exceptional thermal performance, passive humidity regulation, and robust fire resistance, all while just presenting a totally conventional facade to the street. If we step back, the broader implication here is a paradigm shift in how we approach housing resilience and affordability.
Absolutely.
We pour immense capital into developing smart homes, integrating automated HVAC systems, complex synthetic moisture barriers, and networked appliances just to manage our indoor environment.
We basically treat the modern home as this sophisticated machine that requires constant technological intervention.
But this system suggests that true innovation might not require more microchips or synthetic composites. It suggests that by deeply understanding the biology and physics of one of our oldest materials, we can engineer a structure that passively manages its own climate and structural integrity.
Which leaves you wondering, as we look for scalable solutions to massive housing shortages, is the answer more complex engineering or simply scaling up the mechanical brilliance of an adult-sized set of interlocking blocks?